Software process definition. In this video, we are going to see about software process definition. A software process is a set of related activities that leads to the production of a software product. These activities may involve the development of software from scratch in a standard programming language like Java or C. Business software is now often developed by extending and modifying existing systems or by configuring and integrating off-the-shelf software or system components. There are many different software processes, but all must include 4 activities that are fundamental to software engineering: software specification, software design and implementation, software validation, software evolution. Software specification. Software specification is the functionality of the software, and constraints on its operation must be defined. Software design and implementation. Software design and implementation is the software to meet the specification must be produced. Software validation. Software validation is a software must be validated to ensure that it does what the customer wants. Software evolution. The above activities are part of all software processes. They are complex activities in themselves and include sub-activities such as requirement validation, architectural design, unit testing, etc. The collection of activities, possibly overlapping, making up a software process forms a feedback system. Feedback has 4 principal forms: software entity measurements, corrective, change, and improvement. There are some supporting process activities such as documentation and software configuration management. The process descriptions may include products, roles, pre- and post conditions, software process models. In this video, we are going to see about software process models. A software process model is a simplified representation of a software process. Each process model represents a process from a particular perspective and thus provides only partial information about that process. For example, a process activity model shows the activities and their sequence, but may not show the roles of the people involved in these activities. In this section, a number of very general process models, sometimes called process paradigms, and present these from an architectural perspective. That is, the framework of the process but not the details of specific activities. These generic models are not definitive descriptions of software processes. Rather, they are abstractions of the process that can be used to explain different approaches to software development. Process frameworks that may be extended and adapted to create more specific software engineering processes. The process models are the waterfall model, incremental development, reuse-oriented software engineering. Lifecycle models. In this video, we are going to see about lifecycle models. Process models, sometimes called process paradigms or lifecycle models or software engineering paradigms. The various lifecycle models are the waterfall lifecycle model, the incremental lifecycle model, the spiral lifecycle model, win-win spiral lifecycle model, Evolutionary Lifecycle Model. Prototyping Lifecycle Model. Object-Oriented Lifecycle Model. The Waterfall Lifecycle Model. In this video, we are going to see about the Waterfall Lifecycle Model. The Waterfall Model, also called as Phased Lifecycle Model or Waterfall Chart, or the oldest model or the classic life cycle, suggests a systematic sequential approach to software development. It begins with customer specification of requirements and progresses through planning, modeling, construction and deployment, concluding in ongoing support of the completed software. The following problems faced when the waterfall model is applied. Real projects rarely follow the sequential form that the model proposes. It is often difficult for the customer to state all requirements explicitly, and the customer must have tolerance. In an interesting analysis of actual projects found that the linear nature of the waterfall model leads to blocking states in which some project team members must wait for other members of the team to complete dependent tasks. It can serve as a useful process model in situations where requirements are fixed and work is to proceed to completion in a linear manner. This takes the fundamental process activities of specification, development, validation, and evolution and represents them as separate process phases such as requirement specification, software design, implementation, testing, and so on. The first published model of the software development process was derived from more general system engineering processes: requirement analysis and definition, system and software design, implementation and unit testing, integration and system testing, operation and maintenance. The Incremental Lifecycle Model. In this video, we are going to see about the Incremental Lifecycle Model. The incremental model combines elements of the waterfall model applied in an iterative fashion. The incremental model applies linear sequences in a staggered fashion as calendar time progresses. Each linear sequence produces deliverable increments of the software. When an incremental model is used, the first increment is often a core product. The incremental model focuses on the delivery of an operational product with each increment. Incremental development is particularly used when staffing is unavailable for a complete implementation by the business deadline that has been established for the project. Like a disadvantage, the incremental model makes the unrealistic assumption that the system as well as software requirements remain stable. Incremental development refers to the process of developing to completion only a part of the requirements at a time. This approach has been used successfully for business information systems. Developing a large, complex software product using this approach may aim to reduce the schedule and make each increment more manageable than taking on the complete product development at one time. Each increment is developed using a waterfall development process. The Spiral Lifecycle Model. In this video, we are going to see about the Spiral Lifecycle Model. The Spiral Model is an evolutionary software process model that couples the iterative nature of prototyping with the controlled and systematic aspects of the waterfall model. The Spiral Development Model is a risk-driven process model generator that is used to guide multi-stakeholder concurrent engineering of software-intensive systems. It has two main distinguishing features. One is a cyclic approach for incrementally growing a system's degree of definition and implementation while decreasing its degree of risk. The other is a set of anchor point milestones for ensuring stakeholder commitment to feasible and mutually satisfactory system solutions. The spiral model is a realistic approach to the development of large-scale systems and software. The spiral model demands a direct consideration of technical risk at all stages of the project and, if properly applied, should reduce risks before they become problematic. The risks here are typically whether or not the goals can be met within the constraints. In round 2, the top-level requirements are developed. In succeeding rounds, the actual development may be done. Some of the advantages of the spiral model are: it could be as effectively for system enhancement as for system development. Most lifecycle models can be considered as a special case of the spiral model. The embedded risk analysis built into the model avoids many of the difficulties that arise in other models. Win-win spiral lifecycle model. In this video, we are going to see about win-win spiral lifecycle model. The win-win model has a provision for system stakeholders to negotiate mutually satisfactory win-win specifications. Customers, developers, maintainers, interfacers, testers, reusers, and the general public are examples of stakeholders. The new features of the spiral model are inserted into the original spiral model. The shaded areas in figure indicate where the objectives, constraints, and alternatives come from during a project. The no shaded areas in the figure are in the original spiral model. The following two major difficulties in the original spiral model to the introduction of win-win model. Origin of objectives, constraints, and alternatives were unclear in the spiral model. Across an organization's projects, the spiral model lacked anchor points to correlate the completion of spiral cycles and an organization's major milestones. It is clear that incorporation of the win-win approach in the software process provides the basis for a unified effort in tackling the essential difficulties of software. Evolutionary Development Lifecycle Model. In this video, we are going to see about Evolutionary Development Lifecycle Model. There are two approaches for prototyping are Throwaway and Evolutionary. In the evolutionary approach, the prototype is built with the idea that it will eventually be converted into the final system. Evolutionary development is based on the idea of developing an initial implementation, exposing this to user comment, and refining it through many versions until an adequate system has been developed. Exploratory development, where the objective of the process is to work with the customer to explore their requirements and deliver a final system. The prototype concentrates on experimenting with the customer requirements that are poorly understood. An evolutionary approach to software development is often more effective than the waterfall approaches in producing systems that meet the immediate needs of customers. The evolutionary approach has two problems. The process is not visible and systems are often poorly structured. The evolutionary SLCM, that is Software Lifecycle Model, consists of planned development of multiple releases of a product. The evolutionary lifecycle model entails continual overlapping of development activities which produce a succession of software releases. The disadvantage of the evolutionary model is that it can be costly if it is assumed that a current release is made with the assumption that it will be succeeded by an improved version of the software later. Prototyping lifecycle model or throwaway prototyping. In this video, we are going to see about prototyping lifecycle model or throwaway prototyping. There are two approaches for prototyping are throwaway and evolutionary. In the throwaway approach, the prototype is constructed with the idea that it will be discarded after the analysis is complete and the final system will be built from scratch. The goal of a prototyping-based development process is to counter the first two limitations of the waterfall model. The basic idea here is that instead of freezing the requirements before any design or coding can proceed, a throwaway prototype is built to help understand the requirements. This prototype is developed based on the currently known requirements. The process model of the prototyping approach is shown in the figure. A development process using throwaway prototyping typically proceeds as follows. The development of the prototype typically starts when the preliminary version of the requirement specification document has been developed. After the prototype has been developed, the end users and clients are given an opportunity to use the prototype and play with it. Based on the feedback, the initial requirements are modified until to produce the final requirement specification, which is then used to develop the production quality system. Prototyping is often not used as it is feared that development costs may become large. The prototyping focuses on producing software products quickly. Software prototypes are produced with limited functionality and performance to make it possible for developers and clients to check the functions of preliminary implementations of system models before committing to a final system. The prototyping approach solves the waiting problem in the waterfall model. Prototyping is iterated to obtain feedback from clients and changes in system concepts. Object-oriented lifecycle model. In this video, we are going to see about object-oriented lifecycle model. The object-oriented, that is OO lifecycle model, describes the software development in terms of the identification of objects used to construct object networks. The OO model prescribes software development in terms of a synergy between abstraction, modularity, encapsulation, hierarchy, typing, concurrency, and persistence. Abstraction hides details and provides simplified descriptions of a system. For example, principal connections between activities rather than all connections. Two principal advantages to the OO approach are: it simplifies software development because it hides complexity, and the development of classes supports multiple instances of objects as well as encapsulation, which leads to reuse. There is a drawback to the OO approach in safety-critical applications which require a design by contract in the construction of reliable software, that is, interfaces between modules of a software system are governed by precise specifications. Rational Unified Process. In this video, we are going to see about Rational Unified Process. The Rational Unified Process, that is RUP, is an example of modern process model that has been derived from work on the UML and the associated unified software development process. The RUP recognizes that conventional process models present a single view of the process. In contrast, the RUP is normally described from three perspectives: a dynamic perspective, which shows the phases of the model over time; a static perspective, which shows the process activities that are enacted; a practice perspective, which suggests good practices to be used during the process. The RUP is a phased model that identifies four discrete phases in the software process. They are inception, elaboration, construction, transition. System engineering. In this video, we are going to see about system engineering. Software engineering occurs as a consequence of a process called system engineering. The system engineering process takes on different forms depending on the application domain in which it is applied. The word engineering is defined as the art of science of making practical application of the knowledge of pure sciences such as physics, chemistry, biology, etc. System engineering is the application of engineering to the design and development of systems. A system engineer or system analyst typically performs the following technical tasks: thoroughly analyzes the problem to arrive at a set of established needs, develops an architecture, specifies system boundaries and constraints, defines functions, establishes a range of system performance values, defines the internal structure of the system, develops mathematical models, makes objective technical decisions, decomposes or partitions a system into logical, integrable elements or subsystems, participates in the process, uses physical performance results. Computer-based systems. Define a computer-based system as a set or arrangement of elements that are organized to accomplish some predefined goal by processing information. The goal may be to support some business function or to develop a product that can be sold to generate business revenue. To accomplish the goal, a computer-based system makes use of a variety of following system elements. Software. computer programs, data structures, and related work products that serve to affect the logical method, procedure, or control that is required. Hardware. Electronic devices that provide computing capability, the interconnectivity devices. People. Users and operators of hardware and software. Database. A large organized collection of information that is accessed via software and persists over time. Documentation. Descriptive information. Procedures. The steps that define the specific use of each system element or the procedural context in which the system resides. Verification and validation. A separate plan is usually prepared for test and integration in large software development enterprises. Verified that the product was designed and developed in accordance with requirement specifications and development standards. Validated that requirements and resulting products satisfy client or customer needs. Verification. Are we building the product right? Validation. Are we building the right product? System engineering hierarchy. System engineering encompasses a collection of top-down and bottom-up methods to navigate the hierarchy. The system engineering process usually begins with a worldview. The worldview, that is WV, is composed of a set of domain DI, which can each be a system or system of systems in its own right. WV is equal to D1, D2, D3, and so on up to Dn. Each domain is composed of specific elements, that is EJ, each of which serves some role in accomplishing the objective and goals of the domain or component. Di is equal to E1, E2, E3, and so on up to Em. Finally, each element is implemented by specifying the technical components CK that achieve the necessary function for an element. EJ is equal to C1, C2, C3, and so on up to CK. System modeling. System modeling is an important element of the system engineering process. To construct a system model, the engineer should consider a number of restraining factors. Assumptions that reduce the number of possible permutations and variations. Simplifications that enable the model to be created in a timely manner. Limitations that help to bound the system. Constraints that will guide the manner in which the model is created and the approach taken when the model is implemented. Preferences that indicate the preferred architecture for all data, functions, and technology. System simulation. Many computer-based systems interact with the real world in a reactive fashion. For this reason, system modeling and simulation tools are used to help eliminate surprise when reactive computer-based systems are built. Modeling and simulation tools enable a system engineer to test drive a specification of the system. Software specification. In this video, we are going to see about software specification. Software specification or requirements engineering is the process of understanding and defining what services are required from the system and identifying the constraints on the system's operation and development. Requirements engineering is particularly a critical stage of the software process, as errors at this stage inevitably lead to later problems in the system design and implementation. The requirements engineering process aims to produce an agreed requirements document that specifies the system satisfying stakeholder requirements. Requirements are usually presented at two levels of detail. End users and customers needs a high-level statement of the requirements. System developers need a more detailed system specification. There are four main activities in the requirements engineering process: feasibility study, requirements elicitation and analysis, requirements specification, requirements validation. Software design and implementation. In this video, we are going to see about software design and implementation. The implementation stage of software development is a process of converting a system specification into an executable system. It always involves processes of software design and programming, but if an incremental approach to development is used, may also involve refinement of the software specification. A software design is a description of the structure of the software to be implemented, the data, models, and structures used by the system. Software validation. In this video, we are going to see about software validation. Software validation or verification and validation, that is V&V, is intended to show that a system both conforms to its specification and that it meets the expectations of the system customer. Program testing, where the system is executed using simulated test data, is the principal validation technique. Validation may also involve checking processes such as inspections and reviews at each stage of the software process, from user requirements definition to program development. Due to predominance of testing, the majority of validation costs are incurred during and after implementation. The figure shows a three-stage testing process in which system components are tested, then the integrated system is tested, and finally the system is tested with the customer's data. Component defects are discovered early in the process and interface problems are found when the system is integrated. However, as defects are discovered, the program must be debugged, and this may require other stages in the testing process to be repeated. The process is therefore an iterative one, with information being fed back from later stages to earlier parts of the process. The stages in the testing process are development testing, system testing, acceptance testing. Software evolution. In this video, we are going to see about software evolution. The flexibility of software systems is one of the main reasons for software being incorporated in large complex systems. Once a decision has been made to manufacture hardware, it is very expensive to make changes to the hardware design. However, changes can be made to software at any time during or after the system development. There has always been a split between the process of software development and the process of software evolution, that is, software maintenance. This distinction between development and maintenance is increasingly irrelevant. Hardly any software systems are completely new systems, and it makes much more sense to see development and maintenance as a continuum. Rather than two separate processes, it is more realistic to think of software engineering as an evolutionary process, where software is continually changed over its lifetime in response to changing requirements and customer needs. Tools and techniques for process modeling. In this video, we are going to see about tools and techniques for process modeling. Notation depends on what we want to capture in the model. The two major notation categories: static model, dynamic model. A static model depicts the process, showing that the inputs are transformed to outputs. A dynamic model enacts the process so the user can see how intermediate and final products are transformed over time. Static modeling, LAI notation. In this video, we are going to see about static modeling, LAI notation. In the early 1990s, Lai developed a comprehensive process notation that is intended to enable someone to model any process at any level of detail. It builds on a paradigm where people perform roles while resources perform activities, leading to the production of artifacts. The process model shows the relationships among the roles, activities, and artifacts, and state tables how information about the completeness of each artifact at a given time. In particular, the elements of a process are viewed in terms of 7 types. Activity. Activity is something that will happen in a process. This element can be related to what happens before and after, what resources are needed, what triggers the activity's start, what rules govern the activity, how to describe the algorithms and lessons learned, and how to relate the activity to project team. Sequence. Sequence is the order of activities. The sequence can be described using triggers, programming constructs, transformations, ordering, or satisfaction of conditions. Process model. Process model is a view of interest about the system. Thus, parts of the process may be represented as a separate model, either to predict process behavior or to examine certain characteristics. Resource. Resource is a necessary item, tool, or person. Resources can include equipment, time, office space, people, techniques, and so on. The process model identifies how much of each resource is needed for each activity. Control. Control is an external influence over process enactment. The controls may be manual or automatic, human or mechanical. Policy. Policy is a guiding principle. This high-level process constraint influences process enactment. It may include a prescribed development process, a tool that must be used, or a mandatory management style. Organization. Organization is the hierarchical structure of process agents, with physical grouping corresponding to logical grouping and related roles. The mapping from physical to logical grouping should be flexible enough to reflect changes in physical environment. The process description itself has several levels of abstraction, including the software development process that direct certain resources to be used in constructing specific modules, as well as generic models that may resemble the spiral or waterfall models. LI's notation includes several templates such as an artifact definition template which records information about particular artifacts. LI's approach can be applied to modeling software development processes. However, to demonstrate its use and its ability to capture many facets of a complex activity, it is applied to a relatively simple but familiar process, driving an automobile. Table contains a description of a key resource in this process, a car. Other templates define relations, process states, operations, analysis, actions, and roles. The initiate box represents the entrance conditions and the park box represents an exit condition. The left-hand column of a condition box lists artifacts and the right-hand column is the artifact state. Transition diagrams supplement the process model by showing how the states are related to one another. LI's notation is a good example of how multiple structures and strategies can be used to capture a great deal of information about the software development process. But it is also useful in organizing and depicting process information about user requirements, as the car example demonstrates. Dynamic modeling, system dynamics. In this video, we are going to see about dynamic modeling, system dynamics. A desirable property of a process model is the ability to enact the process so that we can watch what happens to resources and artifacts as activities occur. This dynamic process view enables us to simulate the process and make changes before the resources are actually expended. For example, we can use a dynamic process model to help to decide how many testers need or when to initiate testing in order to finish on schedule. Similarly, we can include or exclude activities to their effects on effort and schedule. For instance, add a code review activity making assumptions about how many faults we'll find during the review and determine whether reviewing shortens test time significantly. There are several ways to build dynamic process models. The systems dynamic approach, introduced by Forrester in the 1950s, has been useful for simulating diverse processes, including ecological, economic, and political systems. Abdul Hamid and Madnick have applied system dynamics to software development, enabling project managers to test out their process choices before imposing them on developers. To see how system dynamics works, consider how the software development process after productivity. Build a descriptive model or the various activities that involve developers' time and then look at how changes in the models increase or decrease the time it takes to design, write, and test the code. First, determine which factors affect overall productivity. Figure depicts Abdul Hamid's understanding of these factors. The arrows indicates how changes in one factor affect changes in another. For example, if the fraction of experienced staff increases from 1/4 to 1/2 of the peoples assigned to the project, then we would expect the average potential productivity to increase too. Similarly, the larger the staff reflected in staff size, the more time is devoted to communication among project members, communication overhead. The figure shows us that average nominal potential productivity is affected by three things: the productivity of the experienced staff, the fraction of experienced staff, and the productivity of the new staff. Thus, the first step in using system dynamics is to identify the relationships based on a combination of empirical evidence, research reports, and intuition. The next step is to quantify the relationships. The quantification can involve direct relationships such as that between staff size and communication. If n people are assigned to a project, then there are n into n minus 1 by 2 potential pairs of people who must communicate and coordinate with one another. For some relationships, especially those that involve resources that change over time, so assign distributions that describe the building up and diminishing of the resource. For example, it is rare for everyone on a project to begin work on the first day. The systems analysts begin and coders join the project once the significant requirements and design components are documented. Thus, the distribution describes the rise and fall of the resources. A system dynamics model can be extensive and complex. For example, Abdul Hamid's software development model contains more than 100 casual links. He defined 4 major areas that affect productivity: software production, human resource management, planning, and control. Production includes issues of quality assurance, learning and development rate. Human resources address hiring, turnover, and experience. Planning concerns schedules and the pressures they cause, and control addresses progress measurement and the effort required to finish the project. Because the number of links can be quite large, system dynamics models are supported by software that captures both the links and their quantitative descriptions and then simulates the overall process or some sub-process. The power of system dynamics is impressive, but this method should be used with caution. The simulated results depend on the quantified relationships, which are often heuristic or vague, not clearly based on empirical research. Properties of process modeling tools and techniques. In this video, we are going to see about properties of process modeling tools and techniques. Facilitates human understanding and communications. The technique should be able to represent the process in a form that most customers and developers can understand, encouraging communication about the process and agreement on its form and improvements. The technique should include sufficient information to allow one or more people to actually perform the process. And the model or tool should form a basis for training. Supports process improvement. The technique should identify the essential components of a development or maintenance process. It should allow reuse of processes or sub-processes on subsequent projects, compare alternatives, and estimate the impact of changes before the process is actually put into practice. Similarly, the technique should assist in selecting tools and techniques for the process, in encouraging organizational learning, and in supporting continuing evolution of the process. Supports process management. The technique should allow the process to be project specified. Then, developers and customers should be able to reason about attributes of software creation or evolution. The technique should also support planning and forecasting, monitoring and managing the process, and measuring key process characteristics. Provides automated guidance performing the process. The technique should define all or part of the software development environment, provide guidance and suggestions, and retain reusable process representations for later use. Supports automated process execution. The technique should automate all or part of the process, support cooperative work, capture relevant measurement data, and enforce rules to ensure process integrity. These characteristics can act as useful guidelines for selecting a process modeling technique for a development project. Tools can help prompt developers about what to do next and provide gateways and checkpoints to assure that an artifact meets certain standards before the next steps are taken. For example, a tool can check a set of code components, evaluating their size and structure. If size or structure exceeds predefined limits, the developers can be notified before testing begins, and some components may be reviewed and perhaps redesigned.